In this lesson, we're going to look at the power of a test. To understand what power is, let's review our two types of errors that can occur in hypothesis testing. So first of all, this is what happens. You either have a null hypothesis that is true or a null that is false. If it makes more sense in your brain then to say, well, if the null is false, then that means that the alternative is true. And then what we do is we either reject or we fail to reject after we do our test. So there are 4 different ways this could play out. Now, if the null is true and we fail to reject, this is a correct decision. Okay? If the null is false and we reject, this is also a correct decision. Right? But when we would reject the null hypothesis and it was true, this is a mistake. Now, we don't necessarily know that we've made this mistake because we wouldn't intentionally make it, and this is known as a type 1 error. Whereas if we fail to reject when the null is false or the alternative is true, this is a type 2 error. Okay? Now, one of the memory tricks I will tell you, if you fail to reject, that is a type 2 error. Focus on that 2 part of it, and it will help you remember, hopefully. Okay, the probability of a type 1 error is your alpha level. All right, that's your significance level. It's something you already know. Well, the probability of a type 2 error is sometimes called beta, and that is also equal to 1 minus the power, but let me talk about power first so that makes more sense. Okay, when we are doing a significance test, what we typically want to happen is for this scenario right here. Typically, you're looking to check a claim if it's in medical research or something, and you want to check. You're hoping that you have evidence that the alternative hypothesis is true. And if this is happening, this scenario here, we assign it a probability, and that's known as the power of the test. I want to point out that you do not need to be able to compute power. It's kind of complicated and outside the scope of AP Stat in order to do this. But power is defined as the probability that a test will correctly reject a false null hypothesis. So that it's this scenario right here. So as I had started to say, these 2 values here would sum to 1. Okay, so 1 minus beta is equal to the power of the test. Some things that are kind of important would be, so if alpha goes up, beta goes down, right? They kind of work opposite of each other. And if beta goes down, then power definitely goes up. So you could almost say that alpha and power work in the same way. And I'm going to help you understand this by doing a simulation. Okay, so we're going to revisit the scenario, and I have to give StatsMedic a shout out here because this scenario is really taken from their resources, so they are awesome. Thank you for sharing the resources. All right, so recall that Mrs. Stoltz's claims she is an 80% free throw shooter. Lauren is skeptical and believes that she is less than an 80% free throw shooter. Mrs. Stoltz's has decided to take another simple random sample of 50 free throws to prove herself. Now, write the appropriate hypothesis for the significance test. Be sure to define the parameter of interest. So I'm stating that my null is, that you guys believe me, that I am really an 80% free throw shooter. But Lauren has a claim. She says I'm not that good. So she is testing that P is less than 0.8, and I would define my variable, and I'm stating that P is the true proportion of free throws made by Mrs. Stoltz's. So we are to describe a type 2 error. Well, type 2 is when you fail to reject, but you should have. All right, so if you fail to reject, but you should have, that meant that the alternative was true. So I'm going to state that Mrs. Stoltzfus is less than an 80% free throw shooter, but we decide, she's telling the truth. So I have written here that Mrs. Stoltzfus is less than 80% free throw shooter. So I'm accepting my alternative, but we decide that she is telling the truth. Now what we're going to do is we're going to run a simulation, but we're going to have something that we don't typically have in real life. But to see this is what mathematicians do, is they assume that maybe they understand the true proportion. So it says, suppose that Mrs. Stoltzfus' true free throw percentage is actually 66%. So that would imply that the alternative is true. Now, if you actually knew that my free throw shooting ability was 66%, you would not be doing any type of significance test. You'd just call me a liar. It's not 0.8, and you would, move on. But you wouldn't, in a real life scenario, you don't know that true population parameter. So we are going to use the website you see on your screen, and we're going to go through the following questions. Now, I encourage you, please, to be pausing the video and open another browser and actually do these questions so that you're seeing it and manipulate the sliders on the left. So I am going to click here so you can see this, and over here on the left, it's telling you that the null hypothesis is, and you can enter a numerical value by clicking this value, and I'm going to make this 0.8. So that's my claim, and you can see that this red normal curve here is now at 0.8. It's centered at 0.8. And we're able to adjust over here the true population parameter. So P sub 0, P naught, is what we are testing. But this true P is something we're never actually going to know, but in this scenario, we're told what it is. So I'm going to adjust my p-value to be 0.66. So there it is, okay? So again, you would never actually see this blue curve, but it helps us understand what power is, right? The other things I can adjust are my significance level down here, my alpha level, and we're testing this at our typical 0.05 or 5% level. And my sample size is right here, 50. I'm making 50 free throw shots, so I will leave that at 50, but if it were different, I would adjust it. Up here, you will see the probability of a type 1 error, a type 2 error, and the power of a test, which is the probability that you will correctly reject a false null hypothesis and then, have convincing evidence for your alternative. Okay, so right now you can see that based on this scenario, the probability of a type 1 error is 5%. It's our alpha level. Our type 2 error is 33%, and notice our power is 67. So the relationship right here is shown between a type 2 error and power. Notice that they're going to add to 100%. Power is 1 minus probability of a type 2 error, 1 minus beta. Okay, so on your notes here, it says, if the alternative is true, what is the probability of a type 2 error, a bad decision? Okay, so the probability of a type 2 error is 0.24. Nope. And I just said nope because I realized I have a wrong thing clicked here. Where it says alternative hypothesis, we need to change this to less than. Okay, now I can, let's see, now I see that the probability of a type 2 error is 0.24 here. So I'm going to change this. Probability of that is 0.24. And the next one says, so if the alternative is true, what's the probability of a good decision? All right, so this is what we're typically looking for. This is our power. So our power is got to be 0.76, and I'll switch back so you can see that, but that relationship is 1 minus 0.24, so I know I've got to be right there. And there I can see it. Okay, so I'm going to show you a couple of different things here. So normally you're looking at the red, and you would be shading in this right here. This is anything below 0.05. Anything in here would be the area in which you reject the null hypothesis. Anything there would be considered statistically significant because it's within your rejection region. All right, now I'm going to switch colors here, or highlight the blue as well. So this right here is the probability of a type 2 error, okay, which again you don't normally know, but this is a great simulation to see it. Now this green region is the power of your test. So we're going to be looking at how can we make our test stronger? What different things affect that? The next question on your notes asks you to explain what this power means in context, so this green shaded region. And it's based on the alternative excuse me, got distracted there, sorry. Let me just read it and I'll go through it. If Mrs. Stoltzfus is a 66% free throw shooter, okay, and that was given to us, there is a 76% probability that we decide correctly that she was exaggerating. So this is a condition that we were given, okay? And we're really describing the probability of rejecting our alternative given that the alternative is true. The last thing we want to do is we want to look at how to changing the sample size, the alpha level, and knowing the alternative true parameter, how does that adjust the power of our test? So if we want to increase the power of our test, how would we adjust each of the following? All right, so let's look at sample size. So that's this slider. What happens if I make it smaller? Watch the percentage at the top of the screen. It dropped. So if I go and make 125 free throw shoots, there it went up to 97. So if I increase my sample size, so increase n, that's going to increase power. All right, now I'm going to put this back to 50 because I only want to adjust one thing at a time so I can see how that impacts the power of the test. All right, so next we are told to look at our alpha level. All right, well that's our rejection region. So if I made my rejection region bigger, the power of my test would go up, but I'm also increasing the probability of a type 1 error. So there's a trade-off here. So increasing my alpha level, just click over here so you can see that, increase alpha will increase power. Remember, I'm looking at how do I increase power. Now, how about the alternative hypothesis? Okay. So knowing this true parameter was 0.66. Watch power again, which is right here. Let's say if I make this lower, look, okay, it's further away. If my p-value is further from my p-naught, the power is going to go up. Well, there's no way you can really control that, but it's a good thing to conceptually understand. So one way of stating this is I'm increasing the distance between P and P naught. You will see this referred to sometimes as effect size. If you increase the effect size, meaning the distance between your null hypothesis and the true parameter, you will increase the power of your test. All right, so just to quickly wrap up with our key ideas. So power is a conditional probability. It's given that the alternative is true, it's a probability that you will correctly reject the null. So when you interpret power, you always do this in your explanation to get full credit. So you're saying if the alternative is true, at a specific value in context, there is a, whatever the power is and that will have to be given to you. You don't have to calculate it. There is like an 80% probability of finding convincing evidence to reject the null, but you want to state it in context. And let's just recap our things that would increase power. So if you increase your sample size, if you increase your alpha, if you increase your effect size, which is your distance between your null and your alternative. And then one thing that sometimes pops up would be if you decrease the spread of the distribution. So like your standard deviation. spread of your distribution.